Join us on Tomorrow's World today as we journey through the worlds of inspiration, creation, innovation, and production to find the ideas and technologies that are shaping our future. In part 3 of this 4-part exploration, George sends Greg to explore how small modular reactors can help provide power to remote locations or during natural or other major outages.
Hi everyone, I'm Greg Costantino. Thank you for joining us as we continue our exploration of nuclear energy. Now today, we're going to be talking about small modular reactors, or SMRs, which offer a scalable nuclear power plant solution incorporating enhanced safety, improved affordability, and extended flexibility in both electrical and process heat applications. We're going to be meeting with Dr. Jose Reyes. He is the Chief Technology Officer and co-founder of NuScale Power. And we're going to talk about SMRs and carbon-free electricity. Dr. Reyes.
Greg, so nice to meet you.
Great to meet you as well, and very excited to be here. One of the main reasons being that NuScale Power developed one of the first SMRs to gain Nuclear Regulatory Commission approval. Tell me about that.
Oh, we're very excited about that because that was a critical milestone for us to move forward for construction and deployment of our NuScale plants.
Now, how does this amazing room fit into that scenario?
Well, let me show you. So, Greg, this is module number 2 of our 12-module control room simulator. Everything you need to control the reactor, its operation, startup, shutdown, can all be done and monitored from this panel.
So how many operators do you need to operate all 12 of these reactors?
So we only need 3 operators to control all 12 reactors, and that's very unique. It's about half the staffing or less than a typical large nuclear power plant.
So everything that they need to see in order to operate a reactor, they're going to see on this screen.
That's right. And the reason is it's a very simple design and a very safe design. So over here, we have the reactor vessel inside the containment vessel, which sits in a pool of water below ground. And that really is the majority of our safety system. So the fuel, as it heats up, it will generate flow. So the higher it gets, the more flow you get, so it's kind of a self-regulating system. It's natural circulation. In this design, if you lost all the power to the station, the reactors would shut down without any operator action, any AC or DC power, and they'll remain cooled for an unlimited period of time without the need to add water.
And that's just through general convection?
That's exactly right.
This is exactly the kind of reactor you're going to be building at Idaho National Labs?
It is. So we'll be building a 6-module plant in Idaho Falls. So it'll be a little bit smaller than this 12-module control room, but it'll be identical to that.
Great. Now, I would really like to see how your operators operate.
Oh, absolutely. Come, let me show you. So, Erwin, I'd like to reduce power on module number 11 to 85% power so we can show some of our load following capability.
All right, understand to down power on unit 11 to 85% power. Brock, on unit 11, reduce reactor power to 85% at a rate of 300% per hour.
Understand on unit 11, reduce power to 85% at 300% per hour.
That's correct.
So, Dr. Reyes, when you refer to load following, you're basically talking about the reactor's ability to respond to a need from the grid. So if you're in a situation where you have renewables like solar or wind, and it's daytime and the solar panels are pumping out a lot more energy, the reactor can actually scale itself back and not produce as much as it would under normal circumstances.
That's exactly right. We've worked with 29 utilities in the US and Canada, and they've all said we have renewables, we need to find a way to balance the grid. And so with this flexibility, our load following capability, we're able to balance the grid so that you have a stable grid to work from.
Okay, now, Brock's in charge here. He's in control of this whole simulation.
Exactly right. So you can see the number 3 up there. That means operator number 3, which is Brock. And so he's executed the process for reducing power. We dropped from 77 megawatts down to about 65 megawatts. He's just monitoring the computer programs to make sure that they're executing that process correctly. If you look over here in this pattern, when it's green, that means the control rods are full out. When it changes to yellow, that means that you're inserting the control rods, and that reduces the power. So this gives us a lot of maneuverability so that we could change power to whatever conditions required.
Right. Now, this is obviously a very detailed simulation of what it would be like to operate an actual reactor, but it is a simulation. What do you do to get a real-world idea of where you are?
No, that's a great question. So, of course, this is all simulated with computer models. So what we do is we have a test facility, the NuScale Integral System Test Facility, which is a thermohydraulic test facility, which allows us to produce the data required to benchmark these computer codes. So that gives us a reality check for our simulator. Would you like to see that?
I would love to.
Great, come on. So Greg, this is our NuScale Integral System Test Facility. It represents a 1/3 scale prototype of our entire NuScale power module. So we're modeling the reactor with all of its internals, the pressurizer and steam generator. We're modeling the containment, and we're also modeling the pool itself.
So what we saw on the software side in the control room, this is the hardware version of that.
Exactly right. So here we can actually perform a range of tests at different conditions, at pressures and temperatures, collect that data, and then take that data and compare it to our computer codes.
Now, even though this is a 1/3 size model, when you scale it up to what would be a full-size reactor, how do those numbers line up?
The measured data matches the computer codes very, very well, so we're very pleased with our facility.
Excellent. Now, do you have any other sorts of mock-ups that you used?
We do. We have our upper module mock-up, and would you like to see that?
I absolutely would.
Great, let's go.
So, Doctor, this is the UMM. What does that stand for?
So this is our upper module mock-up, and it represents 1/3 top of our NuScale power module.
So this is something your engineers can use when they want to actually work in the physical space.
Exactly right. So our engineers can develop their maintenance and in-service inspection procedures by using this facility.
Excellent. Doctor, this has been fascinating. Really appreciate it. I'm off to Idaho National Laboratory.
Good luck.
Hey, Yasser.
Hey, Greg, welcome to INL.
Thank you very much. Now, Yasser, in 2017, Hurricane Maria came along and pretty much wiped out all of the power to the island of Puerto Rico. And now, even years later, they're struggling with rebuilding. And the facilities that they had, they were already problematic because of their age. How are microreactors fitting into this conversation about rebuilding?
Well, Greg, as you know, the Hurricane Maria in 2017, when it hit, for several months, the entire island did not have power. Even today, they're struggling with rebuilding some of that infrastructure. But before Hurricane Maria hit, several years before that, we in the nuclear industry, we have been trying to come up with a solution. How do we take really large nuclear power plant technologies and miniaturize them to smaller solutions that we can take from point A to point B very easily and install them and do a plug-and-play installation? Have we had that technology during 2017? I think we would have been able to bring a lot of that power back very, very quickly and provide energy to the grid. Unfortunately, we didn't have that information at that time. I am very excited today to show you what's inside TREAT. We're doing some really exciting things here at INL. Can't wait to show you. So why don't I take you inside and really walk you through some of the interesting things we're doing.
Lead the way.
Okay. Greg, welcome to TREAT. Behind you is a real nuclear reactor.
This is an actual reactor.
Yes, it is.
Wow.
So Greg, you know, we have not really built a microreactor for a very long time for this kind of application, so essentially it's the first of a kind. There are several industry companies that are developing them for commercialization, but before we get there, we wanted to build a very, very quick prototype called MARBLE.
What does MARBLE stand for?
Has a very long acronym, but essentially it's a prototype of a microreactor that's going to produce both heat and electricity. And once we are done with the construction, this is the very pit we're going to be situating the MARBLE reactor to produce both electricity and heat.
So it's not going to be any bigger than this?
It's actually smaller than this pit. We're going to be locating on one end of this area and producing and connecting to applications and testing outside of the building.
Will the whole thing actually be constructed inside the pit?
Well, no, it is a very complicated device. We have not built a new nuclear reactor for about 50 years at the INL. So we have built a full-scale prototype, and I'm kind of very excited to show you that because it is exactly the same as the main reactor.
So I'm actually going to get a look at Marvel.
Yep, I want to take you to the machine shop and actually show you what that looks like.
Okay.
Okay. So Greg, there's been tremendous amount of innovation in the nuclear industry, and so for the Marvel reactor, we really pulled a lot of those cool technologies and made a very simple but yet elegant design. So what you see here is a full-scale replica of the actual reactor. The only difference is instead of nuclear fuel, we are basically using electrical heaters to mimic the performance of the overall system.
Okay, now how long did it take you to put this whole thing together?
So from ideation to coming up with the design and actually fabrication and assembly, it took us only 9 months to get there. And that very speed was extremely important to us because we wanted to really demonstrate how quickly we can go through the process so that some of the commercial designs that are out there can also go that quickly and provide a solution for situations like what we have seen in Puerto Rico with Hurricane Maria, as well as power some of the remote towns and villages that require clean, reliable energy at Alaska.
Wow, that is amazing and excellent. And speaking of Alaska, we're going to check in right now with Senator Lisa Murkowski.
Sounds good.
Nuclear is not only a clean energy, it's that base load energy that is so necessary when you have intermittent sources such as wind and solar. And so when I raise the opportunity for small nuclear, for micro reactors in a place like Alaska, I will tell you, most of my constituents look at me a little bit puzzled, saying, Lisa, wait a minute, we have everything else. Why do we need nuclear? Think about the prospect that could come when you have micro reactors. I kind of describe it, the concept as, you can do this add-on, build-on, Lego type of a concept, depending on what your power needs are. But you can place these in remote areas. You can place these in areas where you have so little to offer currently. And it's not just for resource opportunity. I think about the small communities relying exclusively on diesel. You want to talk about your dirty source, and it's because they have no other option right now. What about the promise, the opportunity for what advanced nuclear holds with, again, the small reactors, the micro reactors, and the ability to help these communities be able to again, keep lights on, keep your place warm.
New types of reactors can bring energy to remote parts of the world or disaster areas, but they can also decarbonize certain industries. I'm going to meet with Shannon Bragg-Sitton of the Idaho Falls Energy Systems Lab to learn more about decarbonizing hard-to-reach areas. Hi, Shannon.
Hi, Greg. Nice to see you, and welcome to the Idaho National Laboratory Energy Systems Lab.
Thanks for having me. I'm very excited to be here. Now, I know, Shannon, that the goal with this is not necessarily for nuclear energy to be the only alternate source of energy out there, but it is going to be a big part of decarbonizing remote and hard-to-reach areas.
That's absolutely correct, and we do a lot of research to look at that. So let's go down the hall and take a look at the laboratory.
Sounds great.
You know, Greg, there's no single energy source that can meet all of our energy demands the same in each location. It's really about finding the right energy mix, specifically a clean energy mix, including wind, solar, and nuclear, to reliably and affordably meet those demands in each location. So Greg, welcome to the Systems Integration Lab. Over here on your left is what we like to refer to as the brains of the laboratory. And that's because this is the hardware that we use to represent power systems in the grid. Using this facility, we can represent how our energy systems operate within a very small microgrid or within a part of a much larger grid balancing area.
Okay.
And over to the right is sort of the heart of the laboratory. And what I mean by that is this equipment helps us to understand how we can bring in all those diverse energy sources together within a single energy park type of configuration and understand how we distribute that energy in real time to meet a variety of energy demands.
It really feels like we're in the middle of an energy producing power plant.
Well, you kind of are. So let's go walk in and see a little bit more.
Okay.
So the goal of any power plant is to produce electricity, and some generators produce that electricity directly, like solar photovoltaics. But a plant like a nuclear plant is actually a thermal power plant, meaning it primarily produces heat that then must be converted to electricity.
Well, how efficient of a process is that? Is all of that heat used in the production of electricity?
Our power plants today are only about 30 to 40% efficient, which means when we convert to electricity, about 60% of that heat that's generated is actually rejected to the environment.
So it's just not used at all, it's just sent out into the atmosphere?
That's correct. And so some of the work that we're doing today in this laboratory is about how we better utilize that heat. So let me show you how we're doing that. On my right is a microreactor emulation testbed. What that means is we represent a very small nuclear reactor and how that heat is then distributed to other energy users.
So this isn't actually a nuclear reactor?
No, what this testbed allows us to do is use electric heaters to represent the heat that would be produced in nuclear fuel. So it looks like a reactor from the system perspective, and then we deliver that heat to a thermal energy storage system behind me, and to a distribution system that allows me to send that heat to energy users.
Now, how do you do that? How can you store heat for any appreciable length of time and then shift it off to some end user like a chemical plant?
Well, how you store it depends on the temperature and the time frame that you'd like to store that heat. That could be molten salt storage, concrete storage, or what we have here is a thermocline energy storage system.
Is this only applicable to nuclear energy?
No, it really just is about managing heat. So that means it's applicable to any thermal generator, such as a concentrated solar plant or even a fossil plant with carbon capture.
Okay, now that leads me to my next question. What other kinds of energy sources are you working with here in the lab?
Well, we've talked about heat, and we can convert that heat also to electricity, and those two things are necessary to produce hydrogen. So let's go look at what we're doing for hydrogen. So over here is one of our hydrogen test beds where we are using water to break it down in its constituent units of hydrogen and oxygen. Over on my right is a water purification system that takes water in and makes sure that we don't have impurities in that water before we produce it to steam. And that goes into this chamber behind me that then is broken into that hydrogen and oxygen in something called a solid oxide electrolysis cell.
Okay, now what are the advantages or why use hydrogen?
Well, hydrogen is an extremely versatile energy carrier. And what I mean by that is that we can put all this hardware down and produce that hydrogen by that power plant, by that source of heat and electricity, and then we can store it and transport it to a number of different end users. And hydrogen can be used to produce electricity when it's needed, or it could be used to power a fuel cell vehicle where then the only byproduct is water vapor, or even in steel manufacturing where going by this hydrogen-based process can reduce emissions by as much as 90% relative to today's practices.
That's amazing. Now, what are the advantages of this method as opposed to other methods that we've used for ages to break down hydrogen?
The traditional approach to producing hydrogen is a method called steam methane reforming. And what that basically means is we take natural gas, we combust some of that to produce the heat necessary to break down more natural gas into hydrogen and carbon dioxide.
which we definitely don't want to do. We don't want to add any more carbon emissions into the atmosphere than necessary.
Absolutely. And when we go about producing hydrogen using either water electrolysis, which occurs at lower temperature, or steam electrolysis, we only produce hydrogen and oxygen.
Is that oxygen then capturable and usable as well?
Absolutely. And we're working with a number of industry partners now to better understand how we can use that oxygen as well to support those chemical processes.
Now, this all sounds like upside, except for the fact that there are portions of the world that are experiencing droughts and actually don't have access to fresh water. Do we really want to be breaking that down?
You know, that's a great point. And that's another application of these integrated energy systems where we can use that clean heat and electricity to purify water and increase water supply in those regions.
So you could take a microreactor to one of these remote locations and literally change the entire structure of that society by giving them access to consistent power and clean water.
Absolutely. And we can do so in a way that allows that power to be available when it's needed, where it is needed, and maintain affordability as well.
Shannon, thank you very much. This has been amazing. And thank all of you for being with us as we continue our exploration of nuclear energy. And be sure to join us on our next episode as we continue to look at this amazing technology and where it will take us in tomorrow's world. For Tomorrow's World Today, I'm Greg Costantino.